Thank you to David and Ran for the kind invitation to speak as part of this series, even though I'm a bit of an outsider or newcomer to this area, but I've been working kind of intensely on trying to understand artificial deep neural networks for some number of years now, and trying to kind of build scientific foundations for deep learning specifically, which has a longer history in this field in neuroscience and machine learning. So the talk I want to give today is going to be just focused on artificial deep neural networks. I'll specifically focus on some more recent work dealing with scaling properties of these networks after learning. So essentially their generalization ability and what dictates that. But we'll do a little bit of theory that I'll discuss, and also try to connect to ideas around data manifolds, and also exhibit one kind of universality that appears in this study that I think is useful just to keep track of. So just to dive right in on the specific thing that I want to talk about today, I want to talk about the generalization ability of deep neural network models, or what in some of the recent empirical literature in machine learning has been referred to as scaling laws, or alternatively, they're really just learning curves. So all of those sort of allude to the study of the same quantity. It's a classic problem in machine learning. And also any other biological system or biological neural system that learns. So what is the given some learning problem, what is the sample complexity of an algorithm or a system that learns? Basically, how many samples do I need to get some amount of error in prediction? And I want to investigate this question, this question kind of broadly in light of these recent observations in deep learning that have kind of come back to the forefront, which are coming from experiments on very large neural network models, where they look at the test loss of, in this case, a very large language model, and they just see that it tends to improve quite monotonically, typically as a power law, as a function of any of the basic kind of tunable variables in the problem. So including the amount of data that the model is trained on, the number of parameters in the model, and also just generally the amount of compute, which is some combination of these and also includes time in it. And all three of these have kind of been observed to exhibit these power law behaviors. So we wanted to use, some theory and some experiments to better understand what's happening here. Where do these trends originate from, and can we kind of be able to classify some of these different scaling regimes? I also want to leverage a little bit of some other developments that have happened in deep learning in the past few years in the theory of deep learning, which have come from new kinds of exactly solvable models for artificial deep neural networks. And this has kind of been some of my own older work. One of the things that the community has learned is, for example, that deep neural networks behave as kernels or as linear models with particular sets of random features as you make the size of the hidden layer of the neural network larger. I'll come back to this later in the talk, but this is kind of just alluding to some of my earlier work and work done by others as well. And I'll talk a little bit about the strengths and limitations of these solvable models. But they are useful in that they also enable us to do theory. They're one of the kind of specific places where theory can be tractably done. And I'll get into this a little bit later. And so in this talk, I want to talk about generalization ability really as a function of multiple variables. And these variables could be the ones I alluded to on the last slide. So the number of samples we have access to, the size of the model, the number of learnable parameters, P, or the amount of computer time. So some of my own motivating questions, why do these trends emerge empirically, and what features of the data and the model affect scaling? Another question, is there any relationship or connection between how a system scales in terms of amount of data versus how it scales in terms of the number of parameters in terms of the model size? Are these completely, distinct, independently? Are these two kinds of trends independently driven, or are they driven potentially by the same underlying quantities? Are there aspects of scaling that can exhibit universal behavior? When does this happen? Why? And I will say there is a lot of literature deriving both within older statistical physics of learning literature, as well as in theoretical machine learning, which is quite much more mathematically involved. There's a lot of work attempting to derive either average case or worst case bounds on different types of learning problems. But for this specific setting of neural networks, can we try to have like a clearer, maybe overall picture of different scaling regimes? Is there a taxonomy, essentially, that could be useful for understanding scaling, rather than, having to derive new results for every problem, depending on the specific situation we're in? And part of what we hope to accomplish with this work was to develop this a little bit of a taxonomy that could be useful. So the setting I want to consider is the classic one that you may be very familiar with, which is that we want to learn a model F of X, and theta are the learnable parameters. We have some data distribution P, and we only have access to the training set. There are capital D number of samples of the XY pairs, and we'll formulate an empirical risk or empirical loss. In my case, let's just think about square loss for now, but some of the results just carry over to more general losses. They're not dependent on that. We optimize this loss to get the optimal weights, and therefore the predictor, and then we evaluate the error in this way, which is the quantity we actually want to be low. Now, just to have everybody on the same page, let's keep in the back of our mind, let's just think about a vanilla deep neural network, but really a lot of what I'll talk about can be extended or is applicable to other architectures as well because of these solvable models that I'm alluding to. But there's a depth L in the computation, and there's this hidden layer with N that are important architectural aspects of the problem. And in this talk, I'm going to be playing with N as a tunable variable to understand the effects of scaling. The type of answer or kind of theoretical result that we are able to derive is to kind of be able to say something about the power law expansions of the test loss. So let me just say a bit more about what I mean. So the quantity that we want to look at, I mentioned there's this test loss, which is a function of this learned optimal set of weights, theta hat coming from the optimization. We want to average over the draws of the data set D, capital D, curly D. And we also want to average over other sources of randomness in the problem, just to have a clean, fully averaged formula. So in this problem, there's also an initial condition theta naught before you start optimization. We're going to average over that as well so that we just have a fully averaged quantity. And I'm going to call that just this big L, and it's a function of these basic variables that I mentioned. So the amount of data that you have in the learning problem, the model size, P, and in principle, the amount of compute or time, but right now we're just going to focus on these two variables already, and I'll talk about extensions. I'll mention a bit of extensions at the very end. Now, P, which is the number of learnable parameters in the network, can increase either by increasing the depth or the width of the network. And as I mentioned, I'm going to focus on just studying the effect of the width right now, because that's one of the variables in the learning dynamics of neural networks that we understand pretty well now. There are a lot of different kinds of large N theories that we can try to utilize, and I'm going to utilize one particular one. So what we're going to be able to say something about is the following. If I look at now this quantity, the test loss, as a function of the amount of data and the model width, I could either study the D dependence of it, or I could study the N dependence of it. And it has, at large D, it has an expansion that is sort of power law-like. It will turn out to be this way. Similarly with the variable N. And what we'll be able to, a lot of the rest of the talk will focus on just what this power law form looks like in terms of the exponents. That's what we'll get out of the theory. The other constants and so on, we're not able to capture within our theory, but we'll be able to talk about the exponents alpha D and alpha W and say something about their origin in different regimes and kind of build a unifying picture. So let me just show empirically what we can, one of the kind of takeaways, but just demonstrated in terms of empirics. So one of the takeaways is that we can have a taxonomy for different scaling regimes. So, we could either scale D or we could scale N, as I mentioned. So we have a binary choice between those. And each one of those scaling variables could be in a different regime. So relative to the value of the magnitude of the other variables. So there's a large data set regime when we scale data, where data is much larger than in kind of the scale of the width. And then there's the reverse, where the amount of data is smaller than this other parameter. And vice versa with N. N can be, there's a regime where the width is kind of smaller than the amount of data. Again, not alluding to the constant factors here, but just, and then another asymptotic regime where N is very large. And it turns out that essentially the pattern is that when the variable that you're scaling is the bottleneck variable to the problem. So for example, here, N is being scaled, and N is the bottleneck because it's smaller than D. Or alternatively, here in this upper right quadrant, D is being scaled, but D is the bottleneck here because D is smaller than width. So in both of these quadrants, there's a specific kind of behavior. We just termed it resolution limited, because essentially what's happening there, we think based off of the theory and the experiments, is that the bottleneck variable, what it's doing is it's limiting the carving up of the data manifold. So that variable is the one that's bottlenecking your performance, your test loss at that time. And the more you add a unit of D or you add a unit of N, you're better carving out this data manifold. And the rate at which you do that, so is given by this exponent, determined by this exponent alpha D and alpha W, will depend on the specifics of the problem. So they're not necessarily universal. And I'll say a bit more about where they originate from. And then the other kind of high level picture is that in these other regimes, so now just on the diagonals of these four quadrants, the variable that you're scaling is actually no longer the bottleneck. So here what's happening, for example, in this upper quadrant is the width is the smaller of the two variables. D is quite large. We're taking it to be asymptotically large. And there it's really the manifold itself is already limited kind of by what you can do with finite n. So the scaling behavior actually ends up taking sort of just a natural, as you approach kind of the limiting value at large D, it has kind of central limit theorem type fluctuations as you approach that limit. And that's why essentially there's an exponent here that is just a fixed integer value and it's equal to 1. And a similar idea holds when I reverse now the role of the two variables. So at a high level, we've kind of tried to partition this space of scaling into these different regimes depending on what's the underlying driver for the improvement. Is the underlying driver kind of the approach to a limit where you just have like central limit theorem type fluctuations towards that limit? Or is it because there's really a data manifold that's being carved up that has a particular, it's a learned manifold in general, and it's being carved up at a particular rate. And in some settings, we'll be able to say more about these exponents. So I'll try to walk us through that. But in the empirics, you see this behavior on display. So these are just neural networks of different, trained on different kinds of data sets. So these are the different colors here. Both these standard machine learning benchmark data sets, as well as a student-teacher problem, also with different loss functions, sometimes MSE or cross-entropy if it's not labeled otherwise. Also different architectures like CNNs and ERFs. And you see in these diagonal quadrants pretty clearly this exponent alpha equal to 1 on display, regardless of, you know, the type of problem, the data set or the type of model or the loss. And that's, you see this kind of uniform exponent equal to 1, similarly down here. Whereas on these off-diagonal quadrants, you see that different problems have different rates at which they're improving, and it's just variable across from, you know, depending on what the problem is, but we'll dig into that a little bit. Okay. So before I jump into what our theory was examining, let me just have a little bit of an interlude on these large N limits that I alluded to, which are kind of what enables, they're kind of something that we can use in the theory to enable us to do these calculations, and they're kind of part of the new developments of the last few years. So you know, the central challenge of this problem, as you know, is just that we don't really know, we have very few analytic results, relatively speaking, on the learned predictor coming from learned predictor in a neural network after training, just because in general, it's a difficult optimization problem. And apart from very, very simple models, there may not be general forms. Now, one limit that's been useful are these large N limits. And the very, first one that, not very first one, but one main one that's been studied in the past few years is kind of the simplest one that has to do with like having essentially a 1/√n scaling in front of the layer weights of every layer. That's sort of a key, kind of a key element of it. And if you have that particular parameterization for a network, which is very natural, at least a lot of neural networks up till now have been initialized in this way, then in the large N limit, what happens is that an infinitely wide neural network before training maps onto a Gaussian process or a Gaussian field theory in the language of physics, and after training, it actually ends up still remaining a Gaussian process or a Gaussian field. And then another kind of finding that happened was that this 1/√n scaling that I mentioned very much controls the dynamics of the learning as well at large N. And so you can actually also solve the dynamics of the learning, and it becomes essentially the model behaves equivalently to a linear model in its learnable parameters, although still very nonlinear as a function of its input x. An alternative way of saying that is just that the neural network, in general, if you imagined Taylor expanding a neural network about its initial condition, that Taylor series could go up to very high order. It doesn't have an obvious truncation point, but in this large n limit, it essentially truncates to its first order Taylor series expansion. And that's kind of an exact result, and it's approximate as you move away from that. It's also subject to a few constraints on the learning rate. But just to sketch that out in equations, this means that more specifically, at large n, the type of model that we can use to study is the following. It's just a linear model in learnable parameters, so it's linear in theta, but it's some nonlinear and fixed function phi of the input data, so phi of x. For some, and these phi I of x are the random features. They're derived from the network at initialization. So they're coming from the random network. They don't adapt to the data. That is one of the limitations of using this model, as a plugin for the full neural network. But nonetheless, this model, there's a lot you can still learn from this model because the phis themselves are non-trivial in their structure. And that's reflected also in the structure of the kernel that you construct from these features. So the relevant kernel, a relevant kernel in the setting is just one where you take the inner product of these features. I'm kind of skipping over some of the details because there are a few different relevant kernels in this setting, depending on exactly which part of the dynamics we're talking about. But essentially, you can keep in the back of your mind that there is some collection of nonlinear random features. There is a kernel that's relevant that we can obtain from that. And these are connected to the 2-point correlation functions of this Gaussian field theory or the covariance of the Gaussian process that I mentioned. But the takeaway is that because of this emergent linearity at large n, we can solve the problem exactly and write down some exact solutions for the learned model. So with that in hand, what we did was for the theory part, we did something which was kind of natural in the kind of statistical physics of learning literature, which is to look at a student-teacher setting. And in this setting, we can extract these leading terms in the expansion that I mentioned for all 4 different regimes. So what is the student-teacher setting? So the teacher model here generates the underlying samples for us. And we use that as the training data set. The student model learns from this data set, and we focus on student and teacher models that are both in this class that I described. So both the student and the teacher are linear in their parameters, again, with these fixed nonlinear random functions. So here it is written out specifically. So this is the teacher model. It has this collection of features f sub m, potentially infinite, that it uses, and then it has some weights. Here we use just fixed weights omega that are drawn normal and IID for the teacher model. It's a very common teacher model, I think, in this literature. And then for the student model, here we have, again, a linear model. The learnable parameters are theta, and the features that the student uses are some collection, potentially of subset of the teacher features. So they're just projection of those teacher features. So the student has access to all the features that the teacher also is using to generate the data. And then we learn the parameters theta. And so far I've left the collection of Fs open, arbitrary, because we're gonna see what the right assumption is to make on this. It'll show up in kind of the properties of the kernel rather than detailed kind of specifics of how F is constructed. Now, I'll skip over this part a little bit. I'll go over this a little bit rapidly. I mentioned in both of these, in this student-teacher setting, we can derive both these regimes exactly. And this is because you can write down the test error in terms of these different Gram matrices constructed from the features and also the projection matrices P. And skipping over a lot of steps, I'll just say that what I called this variance limited regime, so this regime where the exponents were equal to 1, and the approach to the scaling was controlled by approach a central limit theorem type behavior. The reason we gave it this name was because if you look at if you try to derive the exponents in this regime, what you find is that the behavior is kind of set by looking at these the variance of particular quantities related to the kernels, and these quantities themselves scale as inverse power laws in either the model size or the data set size, depending on which variable you're scaling, with an exponent equal to 1. And because of this, because of the way that these finite kind of finite size covariances approach their limiting values, because this approach is governed by a 1 over x type behavior with exponent 1, that controls the way that the loss approaches its limiting value. So this is why we gave it the name variance limited, and why, regardless of the problem type, at least in this setting, you would see exponent equal to 1, regardless of the data or the task and so on. Okay. What we also find from this analysis is that there's actually a duality between exchanging data and features in these expressions. And essentially what that implies is that the exponent for data scaling and the exponent for the width scaling should be the same in this specific setting. We call this a duality. And you might wonder, well, how specific is this to just your theoretical setup? Does it have kind of credence outside of it? I'll show some numerics where actually, although this prediction on the theory, we only derived it in this setting, there are reasons why it can, I think, you can see it in experiments beyond this simple student-teacher setup with linear models. And now let me talk about what's probably the more interesting regime, which is this resolution limited regime, where I mentioned the rates are problem dependent. And so in this setting, the relevant quantity is actually the eigenvalue spectrum of the kernel matrix. The kernel matrix that's constructed from these features F sub m that I mentioned. And so we have to make an assumption on this eigenvalue spectrum lambda I. So just to reiterate, we formed some kernel matrix from these features by evaluating on the data. And what I think is a well-motivated ansatz that we kind of just took from looking at data with these various types of kernels derived from neural networks is that a power law assumption on the lambda i's seems to be a pretty good assumption. So lambda I going as some power of I, and here in just in anticipation of the result, the exponent is called 1 plus, is just labeled 1 plus alpha k. And if you assume this as your, if you take this as your assumption, then you can derive that the test loss will scale as g to the minus alpha k. So the kernel eigenvalue spectrum, its power law is affecting the data set scaling. And then by this duality, we found it's also therefore affecting the way that the model learns as a function of the number of parameters as well, or width in this setting. Just to compare this to some of the other works that have been looking also at this problem. So at a high level, I wanted to just mention that there are a lot of nice works either looking, both in the older literature, but also more recently looking at student-teacher settings and also kernel regression and so on. as well as other works from a number of statistical physics of learning groups. And I would say that a lot of these works are essentially focusing on one of these sectors in the quadrants that I mentioned. So particularly, a lot of them are looking at this quadrant on the right, where they're looking at the data set size scaling, and the number of parameters in the model is essentially large or infinite. But what we're trying to do is kind of relate these different quadrants to each other, understand if there's a relationship and maybe like a unifying kind of driver behind these different scaling regimes. Now, just to kind of convince you that this power law assumption was a good one, here on the right, let me show you, I'm showing you the eigenvalue spectrum of these kernels. You could take any kernel kind of constructed from either a fully connected network or other architectures. And if you looked at it on real data, real image data, or just data from the natural world, typically the eigenvalue spectrum would have power laws in it at large enough index values. So there's some transient regime here, but typically at larger I, there are power laws, and the strength of the rate of the power law does depend on the properties of the image and the architecture combined in some pretty non-trivial way. One way you can see that the image itself has an effect on what this rate is here what's happening is if you take the images and you coarse grain them, so you just by pooling over receptive fields of different sizes, you can tune the value of the exponent, and therefore, and also essentially the complexity of that learning problem. But just to kind of reiterate, the right assumption, I think, from the more microscopic level in this problem is that is in this power law structure of this kernel, which incorporates both the data but also the architecture. It kind of describes how well it sort of encapsulates how good these are for each other. How good the architecture is for the input data that it's seeing. So that's one of the takeaways. I will skip over this slide. This is more empirical support, kind of in the same vein, just for the showing you more results for the student teacher setting specifically. But I already showed you that these results kind of carry over to the neural network setting as well. But just to maybe summarize what the student teacher setting, what we learned from doing the theory is that in this, going back to these 4 quadrants, we have these exponents alpha equal to 1 on the diagonals. But on the off diagonals, in the specific case of student teacher models, we found that alpha d is equal to the kernel exponent, and alpha w is also equal to the kernel exponent. And this is what we can derive by leveraging these solvable models, specifically in this setting. Now, we can also check some of how this carries over to other settings beyond the student teacher one in experiments. So one pretty common setting is to pre-train a model on some data and then fine-tune the model, for example, by adding just a linear layer for some other data set. And even though this goes beyond our theory setting, so it's not a student teacher setup and it's no longer random features, but it's using learned features from a pre-trained problem, we still find these alpha equal to 1 exponents approximately on these diagonals. But we find that we find these alpha p and alpha, alpha p here is actually alpha w. But these numbers are actually pretty close to one another. So it's an example of this duality that I mentioned, where we find that the 2 exponents for the 2 different resolution limited scaling regimes are actually the same. Now, you may be wondering, what is this peak here that I'm saying that is showing up in the experiments? This is just a double descent peak. that is common in these types of problems as you move from one regime to another. And actually, what we're doing is trying to unify this, our understanding of what's happening on one side of the double descent peak with what's happening on the other. So really, you ought to just focus attention on this leftmost part, and same here. So here with the proper regularization, the double descent peak goes away, and that's why you just see the scaling again. This alpha P and alpha D values being close to one another is a manifestation of this duality that I mentioned. Now, I think in the interest of time, I'm gonna maybe speed up a little bit through this part. I'll just say that when we tried to go to now more general neural networks, so not linear models with random features, but neural networks that really do adapt their basis functions and so on, we tried to see which parts of what we found could be generalized. And the takeaway is that the variance limited regime is generalizable. So those exponents alpha equal to the 1 that I mentioned are things that you could see whether you have a linear model or a neural network that really adapts to the data at hand. But the resolution limited regime, we still lack a general analytic form away from these solvable models that I mentioned that would be easy to analyze for generalization. And so, without this in hand, what we tried to do was we made a few other hypotheses coming from that kind of kernel analysis and student-teacher setting that then we tried to just test in experiments and see if we could tie these all together. And one of those is sort of what you would think is a natural back of the envelope hypothesis for what happens in the resolution limited scaling regime. So, again, just to reiterate, this resolution limited scaling is what's happening in these off diagonal quadrants that I showed you in these different regimes. And let's say you didn't know much about what was happening, what the form of the actual learned predictor was for the neural network, because that's some very complicated function to write down. And we only have these linear models that are essentially the first order Taylor expansions that we can actually analyze. You might try to see how far you can just get with assuming with just smoothness assumptions. A lot of theoretical machine learning does this as well. And skipping over a lot of this text, let me just say that if you were going to look at the test loss, the loss at a particular test point, and suppose you're trying to carve out, resolve the data manifold, some learned data manifold, that captures the data. When you have very many samples, so in the very large D limit, if the manifold that you're trying to describe is compact, then in some very asymptotic regime, when D is very large, you could imagine trying to Taylor expand the value of the test loss at a particular test point in terms of the value at the nearest training point or nearest collection of training points. And so X here is a little bit of a ambiguous. I've left it ambiguous. Really, it's something that would be measured in some learned representation. It could be, for example, an intermediate representation within the network. But you could imagine doing this expansion, and you would expect that if your model is doing perfect interpolation, which a lot of neural network models nowadays do because they're so large, then you exactly are fitting the training points. And if you have many training points, then there's some point at which you have done a very good job, for any test point, you're very close to some collection of training points. And so you could do this expansion and try to understand the leading order term in it. And what you would then kind of assume or find is that probably what happens is that the nearest neighbor training distances as well between data points also go as a power law. So again, just to reiterate, this X here is really, it's like phi of X. I haven't told you which representations exactly I'm measuring. But those themselves would, go as some power law in D. Let me call that defines what this exponent is, 1 over little d. So if I can measure this, I can infer what this exponent is. And then the test loss itself would go as n over d, where n is wherever this series starts. So it could be 2 or it could be 4 if there's some symmetry conditions. And you could make a similar argument just reversing these two variables by looking at the number of parameters. And so in short, one of the hypotheses we had was that maybe a different way of looking at these exponents is really to try to measure or to infer some notion of D by looking at nearest neighbor distances and how they scale and connecting that to the exponent. And this kind of closes the loop on all of these quantities because it tries to relate the the test loss, to both the kernel spectrum, either fixed or learned, as well as the dimensionality of some learned data manifold. And so we tried to do this experimental comparison where what we do is we look at the scaling exponent alpha d measured from just power law fits to the test loss. And then we try to infer some notion of dimension, again, kind of difficult to estimate numerically and so on, but we infer it by looking at these nearest neighbor distances in the penultimate layer of representations in a neural network. So looking at how that scales and trying to correlate these two quantities. And I leave it up to you, the agreement is decent. It's not great, but it kind of shows, I would say, a rough correlation in terms of how these nearest neighbor distances would be scaling and the exponents. And to tie this all together, there's a way to connect it back to, at least in the particular case of kernels, back to the kernel eigenvalue spectrum. Okay, and so that's kind of the maybe the more global picture here, even when we can't leverage these kernel models or linear models, and we're in a regime where neural networks are doing feature learning, they're adapting their bases. At least one of the things that we can say is this variance limited regime really does hold up, as shown on these diagonals. And the resolution limited regime, although we don't have a specific kernel that we can relate our exponents to, we can at least try to connect it to this measure of dimensionality that's inferred from the learned representations. And in those limits that I showed you where we do have linear models, we can derive the exponents. But this kind of helps build a little bit more of a taxonomy or a picture for understanding different scaling regimes when you have multiple variables. You might want to know which regime are you effectively in and what is the what's happening in that regime in terms of the learning process and generalization. I think I'm almost out of time, so I'll maybe skip over to the very end. I'm happy to say more during the Q&A, but just kind of conclude about what we accomplished in this work, which was, trying to leverage these recent results, relatively recent results from theory of deep learning in the large N limit, which gives us some solvable models that we can actually do theory with, try to extract as much insight from that possibly as we can, and then kind of extrapolate to this other regime where neural networks really do learn in a different way, but still there is a taxonomy that remains and can be useful. I will say that, as I mentioned, those resolution limited regimes, we still don't have a full theory for that, and we're working on that. That's something that we're working on right now. And since then, other kind of works have appeared, kind of studying either the same or very related models, still within this linear models random features regime that might be of interest here. So I think I will skip maybe to the end. If I understand, I might be out of time. And maybe just close with a little bit of more of a philosophy, which is that in this talk, and a lot of kind of my own older work, the approach that we've been taking has really been to try to derive results what I would call from first principles. So we actually have a microscopic model of a neural network. As a function of learnable parameters, we're trying to derive something, something about the predictor analytically, and so on. And I think that there's some mileage that can be gained there. But I also start to wonder in these very large models, particularly now with language models and so on, a first principles approach where we really try to go from the very microscopic level to understanding some higher, some more general principles can be challenging. And so maybe there's actually a need to bridge these different scales to maybe have very different starting points conceptually and theoretically, rather than trying to derive using gradient descent and using a depth L neural network all the details of the problem. So I'll just leave that as food for thought. I want to thank my collaborators who were the ones I worked with on this specific project, and just say that if you'd like to read more, not about scaling, but just about some of the earlier kind of general results on dynamics and solvable models in these large width limits, I gave some lectures at Les Ouches that you might find interesting, and they're on the archive. And thank you.